Hi, my name is Vieta, and in this video, I'll be going over Vieta's formula, which I think is a really neat, interesting formula for solving higher order polynomials and when you have a higher order equation. And I think it's really a shame because this formula is very useful, yet it's not taught in most American high schools, which is why I want to make a video on it. So to start, you might know that this case, if we're given a quadratic, the sum of the roots is going to equal b divided by a, negative b divided by a, and the product is going to equal c divided by a. But with Vieta's formula, what we can do is we can expand this definition to any degree polynomial. So let's say we have some polynomial p of x such that the polynomial equals a(n), where a is coefficient, times x to the power of n, plus a(n minus 1) times x to the power of n minus 1, plus blah, 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 right, going all the way to a sub 1 to the power of x to the power of 1, which is just x, plus a sub 0 times x to the power of 0, which is just 1. And let's say this polynomial equals 0, and it has roots r1, r2, all the way to rn. So Vieta's formula states that, first of all, the sum of all these roots, root 1, root 2, root 3, all the way to root n, right? And again, the reason why we have n roots is because we have a n degree polynomial, right? X to the power of n is the highest coefficient, and therefore we're going to have n roots based on fundamental theorem algebra. And so this equals, right, by Vieta's formula, this equals negative a(n minus 1, so the first coefficient, or second coefficient, divided by a of n. Okay? Secondly, we have more equations, right? Our second equation would be, and notice first of all that this is negative, okay? Second equation is going to be r1 times r2 plus r1 times r3 plus r, and we're going to keep doing that, plus r1 to rn. So what we're doing is we're taking r1 times r2, r1 times r3, r1 times r4. We're doing that for all the way up to rn. Next, we're going to add that to r2 times r3 plus r2 times r4 plus, and all the way again to r2 times rn. And we're going to keep doing this for every number until we reach, eventually, r times n minus 1 times r of n. Okay, so we're going to keep doing that until we reach there. And this is equal to a(n minus 2 over a of n. So it equals the third coefficient, right? There'd be coefficient after this, divided by the first coefficient, and this one is positive. So already we can see the pattern, right? We're switching negative, positive, negative, positive. The next one, which is going to be r1, r2, r3, plus r1, r2, r4, plus, and again, we'd be going on until we reached rn minus 2 times rn minus 1 times r of n. This is equal to negative a(n minus 3, so the fourth term, coefficient, divided by a of n, and this one's negative, right? So again, we see the alternating thing happening here. And so we can keep doing this until we reach a point where we have r1 times r2 times r3 all the way to times rn. Right, so when we reach this point, we have no more equations and we stop there. When we reach a point where r1, r2, r3, all the way to rn are just being multiplied together in one term. And this final term is going to be equal to negative 1 times n, negative 1 to the power of n, times a sub 0 over an. Right, and so what does this term mean? This term is different than what we had before. But the idea is, right, so we can call this step 1, or equation 1, equation 2, equation 3, right? So when we have 1 as our n, we get negative in our term. So negative 1 to the power of 1 is negative 1. When we have 2, we have positive. Negative 1 to the power of 2 is positive 1. Therefore, it's positive. So the idea with this is it's going to make sure that our final term is correct in terms of sign, and it does so using this negative 1 to the power of n term. And then the final thing is we're multiplying by a0 of a of n, which means we're multiplying by the last coefficient divided by the first coefficient, and that equals the product of all the roots. Okay? So that's Vieta's formula, and as you can see, this formula works for this case, right? So in this case, we only have, we're going to have two equations, right, because we're doing only to the power of 2. The first one, r1 plus r2, is going to equal, right, the second term divided by the first term, and negative, right, because it alternates. So negative b over a. Second term is just r1 times r2, right? And we have no more equations after this. but it's going to be equal to c divided by a, right? The last term divided by the first term. We can expand this now to quadratics, or sorry, cubics, using Vieta's formula. Okay, so let's say we have a cubic like this, right? R1, R2, R3 as the roots. So we know that R1 plus R2 plus R3 is equal to negative b over a. We know that R1 times R2 plus R1 times R3 plus R2 times R3 is going to equal to c over a. And it's positive because we're alternating signs. Finally, we have R1, R2, R3 as our final one. It's going to equal to d over a, but negative because, again, we alternated signs. And if we use this formula, negative 1 to the power of 3, right, third equation, it's going to be negative 1, so negative d over a. And so you can really see the power in this, right? Because we did this with the quadratic, we did this with the cubic, and we can keep doing this for any term, x to the power of n. We can do it for any kind of higher order polynomial. It's really powerful because, again, we have three equations now with three variables, so we can now solve it using this, or we can otherwise manipulate it and try to figure out stuff using the roots. And let me just go through a quick kind of proof, sort of, a short little one, of course. And I'm just going to show you guys why this really works to some extent, right? So let's just prove the quadratic one first. So let's say we have a quadratic a times x minus r1 times x minus r2, and this equals 0. So we know the solution for this quadratic is going to equal to, right, because we just factored it, root 1 and root 2. Okay? So I'm going to do here, I'm going to expand it. So if I expand first, distributing, right, I get that a times x, x squared, minus r2x minus r1x plus r1 r2 equals 0. I can then expand the a, so ax squared, minus, and here I have a negative of an x. I can kind of factor that a little bit, and what I can do is I can say, okay, this is equal to negative a times r1 plus r2 of x plus a r1 r2 equals 0. Okay, so this is obviously our a term, right? But here we can see that before, when we said our b, right, here, right? So ax squared plus bx plus c equals 0, right? Our b is going to be whatever is in front of the x term, which is this coefficient, right? So we say that negative a times root 1 plus root 2 is equal to b. Here we say whatever is then added, the constant term, is our c. So a, r1, r2 is equal to c. And now you can simply see that in this case, if we divide by negative a, we get the r1 plus r2 is equal to negative b over a, and r1, r2 is equal to c over a. And so we kind of just proved Vieta's formula works for quadratics. And we can do the same idea for cubics, right? We would just have another factor, and we would just expand it, and we could do the same exact thing. We could do the same thing for any order polynomial, and we get the same kind of result. And one interesting thing, too, is the reason why we divide by the first term always is because you can see, right, in each of our terms, right, we have an a, we have an a, we have an a, which is exactly why we divide by an a to, again, get rid of this a and figure out our r1 and our r2 roots. So let's do one quick problem just to show you guys why this formula is useful, and then we'll wrap it up. So let's say we have the equation 2x cubed minus 2x squared minus 28x plus 48 equals 0. And we know they're saying that the roots a, b, and c. These are the roots, a, b, and c. And they're asking us to solve what is a squared plus b squared plus c squared. So what is the sum of the squares of the roots? Okay, and again, these are roots. Okay, so first things first, I don't really want to try solving this, right? Because there's nothing really easy I can do for solving it beyond using kind of rational root theorem to try to guess and check. So because of that, I'm going to try using Vieta's formula. So I know that a squared plus b squared plus c squared, that kind of looks like a plus b plus c squared, right? Sort of. Right, so what if I expand this, right? A plus b plus c squared, right? So we know that a plus b squared is equal to a squared plus 2ab plus b squared So we can say that, okay, this is just the same thing as a plus, and we'll put these in parentheses, b plus c squared, right? So we can call this b basically. And we can then say that this is equal to a squared plus 2 times a, right, times b plus c, because we're just doing, again, this formula, plus b plus c squared. Okay, so we get a squared, right? So we can move the, distribute the a, we get 2 times ab plus ac plus b plus c squared. This is b squared plus 2bc plus c squared. Again, we're just expanding it. And then we can collect the terms. So a squared plus b squared plus c squared, we recognize that as what we want, a squared plus b squared plus c squared. But then we also have this kind of excess term, 2, right? So 2bc, we can then factor that into 2ab plus ac plus bc. And what we recognize is, oh, our answer that we want here, right? Call this answer like x, right? Our x term is here, but we also have this kind of residue here, 2ab plus ac plus bc. Well, we know how to find this, right? We can use Vieta's formula to find what this value is. So using Vieta's formula, ab plus ac plus bc, right, that's going to be our second equation, is going to be equal to negative 28 divided by 2, which is equal to negative 14. And it's going to be a positive term, right, because our first one's going to be negative, then it's going to be positive, so negative 28 divided by 2. We don't do include a negative, and so we just get negative 14. Okay? Therefore, what we have, right, so we have our what we want, x, plus, again, 2 times this value, so 2 times this value is negative 28. And then on the left-hand side, we have a plus b plus c squared. And so we also know what a plus b plus c is too, right? So a plus b plus c is going to be equal to our first term, negative 2, divided by 2 times negative 1, because it's the first one, so we get 1. So a plus b plus c squared is going to be 1. So 1 is equal to x minus 28. Therefore, if we move the 28 to the other side, x is equal to 29. And our answer for a plus b plus c squared is going to equal to 29 using Vieta's formula. So again, this really just shows the power of Vieta's formula, because instead of having to solve this kind of complicated cubic, we were able to simply just kind of figure out what the roots would be, or figure out how to take this equation and put it in terms of parts that we knew to find using Vieta's formula. And yeah, that's it for today. Thank you guys all for watching, and I'll see you guys all tomorrow. Bye.